In this lesson, we're going to start looking at the normal distribution, which is going to be a distribution that we use for almost every chapter in the rest of the course. So we're going to start off here with some properties of a normal distribution. First of all, it's going to be symmetric, so mirror image from one side to the other. It's going to be bell-shaped, and it's going to be centered about its mean. So when we say it's symmetric, that point at which it is a mirror image on one side versus the other centers around the mean. So normal distributions can differ from one another with respect to their center. So we just talked about that center was their mean. So if they have different means, they'll be centered in different locations on a number line. And then also their variation, which is a reflection of how much spread there is in the distribution. We measure variation with standard deviation. So we have some notation here which tells us that a variable x follows a normal distribution, and if it does, we write it this way. So x is distributed normally with mean mu and standard deviation sigma. So I'm just going to draw for us a few examples of some normal distributions. So we have an axis there, and so we might have a normal distribution that looks something like that. So you will notice that along this axis, I'm just going to call it x, we have this bell-shaped curve. It's symmetric, and the point at which it is symmetric about looks like it's about right here, and so that would be the mean. I'm going to draw some other examples of normal distributions. We talked about the fact that there could be infinitely many of these based on their mean and their standard deviation. So there's another one. You'll notice its mean is going to be right here on the number line, and its standard deviation is going to be larger than the standard deviation over here. That's because it has more spread, more variability in the possible data values. And then let's draw one more that has very little spread. Okay, so you'll notice this last one I drew is the tallest one. It's also the narrowest. So being the tallest and the narrowest means that it has the least spread, the smallest standard deviation. So I'm just going to call these A, B, and C. And if we're moving along a number line where the numbers get larger as we move from left to right, so the numbers get larger, we would notice that C's mean is kind of right around here. B's mean is right around here. A's mean is down here. So those are right underneath the peak of each of those curves. And in terms of ordering the standard deviations, we said that the standard deviation for C is the smallest, so it's less than the standard deviation for A is the next smallest. And then the standard deviation for B, in that case, is the largest because it has the most spread, shortest curve, most spread. Okay, so we're going to move on here to start talking about how can we tell if a distribution is roughly normal. So if most data values are clustered near the mean, giving the distribution a well-defined single peak, that's a good indication it might be normally distributed. If the data values are spread evenly around the mean, making the distribution symmetric. If larger deviations from the mean become increasingly rare, producing tapering tails of the distribution. So up here you'll see, right, as we get further away from the mean, we have less and less area underneath that distribution curve. And then finally, if individual data values result from a combination of many factors, such as genetic and environmental factors. So a lot of times if we're measuring something, it ends up being roughly normal. So I gave you an example here at the bottom. It says, which of the two variables below would you expect to have a normal or close to normal distribution? Wages at a fast food restaurant where most workers earn minimum wage. So if we think about that, and I'm just going to draw a rough sketch of a histogram over here. where this is our wage and this is our frequency. It just told us that most of the workers earn minimum wage, so we're gonna have a high frequency down here at a low wage. Most of the workers earn that wage, and then we might have maybe a manager or a supervisor that is gonna earn a little bit more, but not much in between. You'll notice that is not, when we try and fit a curve here, that is not a nice normal bell-shaped curve. Okay. Our other choice is head circumference for a random sample of 12-month-old infants. So again, just quick sketch thinking about head circumference and frequency. And so as we all know, there's kind of an average head size, and you can tell just by looking at babies, right, that they all have kind of around and the similar size head. There's definitely variability. Some are a little bigger, some are a little smaller. But this is a case where we would probably have a more common size, and then we might have some variability or some spread around that. And you'll notice that would give us more of this bell-shaped curve. Okay, so in terms of those two variables, which one would we expect to have a normal distribution? The head circumference one would be the one that might fit. Okay, as we're moving on here, I'm still talking about normal distributions. We need to talk about a little bit more about where the area under the curve is most heavily populated, and then what happens as we get further away from the mean. So we're going to start by looking at this empirical rule. This is also called the 68, 95, 99, 7 rule, which you'll see why in a second. So the first property of this rule tells us that about 68% of all of our data values are in a normal distribution are going to fall within one standard deviation to either side of the mean. So what you'll see here is I've drawn a normal distribution curve. I've labeled along the horizontal axis our center, which is at that population mean, mu. And then you'll notice I've added both 1, 2, and then 3 deviations above that mean, as well as 1, 2, and 3 standard deviations below the mean. And we've just got things labeled. So that first property tells us that if we look here within 1 standard deviation below the mean to 1 standard deviation above the mean, that area there between 1 below and 1 above is about 68%. If we go out and we add more of the area under the curve, by the time we get out to 2 standard deviations below and above the mean, we are now looking at an area of 95%. So 95% of our observations we would expect to fall within 2 standard deviations of the mean. And then by the time we get out to 3 standard deviations above and below, you'll notice now we've captured 99.7% of the data points, so almost all of the data is going to fall within those 3 standard deviations. Okay, we're going to look at an example where we apply that rule. So this next example says the body mass indices, BMIs, of American men between ages 30 and 50 are normally distributed with a mean of 26.2 and a standard deviation of 4.7. And we're supposed to use the 68, 95, 99, 7 rule to fill in the area of each region below. So I'm going to start here labeling our horizontal axis X, where X is measuring our body mass index. The distribution of body mass indices we drew as a normal bell-shaped curve because it told us that the body mass indices were normally distributed. The center we know is going to be at the mean, which we were given is 26.2. And the standard deviation is 4.7. And so what that tells us is that each time we add another standard deviation or subtract another standard deviation, we're going to do that in increments of 4.7. I'm going to label these actually down in the white so you can see it a little bit better. So there's our mean at 26.2. From that mean, if we want to go up one standard deviation, we're adding 4.7. That gets us to 30.9. If we add another copy of that standard deviation, so we add another 4.7, that gets us to 35.6. And then one more gets us to 40.3. And then we would do the same thing in the other direction. This time, instead of adding increments of 4.7, we're going to subtract increments of 4.7. So we would have 21.5, 16.8, and 12.1. Okay, and just a heads up at this point, typically when we're asked to draw a normal distribution curve, this is what we would want to draw. So we'd want to draw the bell-shaped curve. We would want to show that its center was at the mean. And then we would want to show that we had labeled each of those increments of the mean plus 1 standard deviation, the mean plus 2 deviations, the mean plus 3 deviations, and then subtracting also in the other direction. Okay, so that's what we're going to do when we're asked to draw a normal distribution. You'll notice this one asked us to use that 68, 95, 99, 7 rule. So we're just going to divide up the curve a little bit more. What we're going to label this time is, instead of labeling values of BMIs down on the horizontal axis, we're going to label areas up here in the body of the curve. Okay, so one thing that we know from that 68, 95, 99, 7 rule is that 68% of all the values are going to fall within 1 deviation to either side of the mean. And if we know the curve is symmetric about that mean, that means that that 68% is divided into 2 equal halves, each having about 34% of the total area under the curve. So again, those two 34% slices sum together to give us the 68. Next, we know that by the time we get out to 2 deviations, we have about 95% of the data. So by the time we're out here and out here, we're at 95. Well, we already know that 68% is here in the middle. So we're gonna take 95, we're gonna subtract 68, and that gives us 27% is remaining. That 27% is split evenly between these 2 slices, okay? So we're gonna divide that by 2, and we get 13.5, and so 13.5% of the area is in each of those next slices. By the time we go out to 3 deviations below and 3 deviations above, we are at 99.7%. We already know we had 95% by the time we were at 2 deviations. So the difference is that 99.7 minus the 95, where we already know that it is. And that leaves us 4.7% left over in just those 2 slices. Again, those are symmetric, so those are equal. We're gonna divide that by 2, and each one of those has area about 2.35% of the total area under the curve. And then finally, by the time we get to the end, right, way out here in the end points, we know that the total area under any distribution curve is 1, so 100%. So 100 minus 99.7 gives us 0.3% that's left over. Divide that into 2 tails, and we get 0.15% that's going to be out beyond 3 standard deviations in either direction.